Okay, we are recording. Let's get started. So L'Hopital's rule is used when we take the limit and we end up getting one of the following. And this is what we call indeterminate forms. So 0 over 0, that's one that we've worked with before. Infinity over infinity, we've also worked with before. And what happens is they don't cancel out to being 1. It's not the same way a 5 over 5 would cancel out to being 1. Infinity, not all infinities are the same sizes, which we talked about when we did infinite limits before. Or infinity times 0, infinity minus infinity, 0 to the 0, 1 to the infinity, or infinity to the 0. So basically, if we get any answer like this, when we take a limit, we can potentially use L'Hopital's rule. So let's do some examples. So let's take the limit as x approaches infinity of 6x squared plus 2x over 5x squared minus 1. So we did a couple examples like this before in a previous module, and what we did is we divided each term by the largest exponent in the denominator. So in this case, we would divide each term by an x squared, and that works perfectly fine, but we could also apply L'Hopital's rule if we get an indeterminate form answer. So if we take the limit, just rewriting, as x approaches infinity, of 6x squared plus 2x over 5x squared minus 1. What happens is the numerator goes to infinity, because we have an x squared and a 2x, that goes to infinity, and the denominator also goes to infinity. So we get infinity over infinity, which is not an answer. So we need to try something else. In the last set that we did in one of the previous modules, we divided every term by an x squared, but we could also use L'Hopital's rule. And what L'Hopital's rule says is, hold on, if we're taking the limit as x approaches a, so a being anything, infinity or a numerical value, of some fraction f of x over g of x. And we end up with one of the forms that we just talked about. What we can do is take the limit as x approaches a of f prime of x over g prime of x instead, and that will give us the value. Potentially, we may have to apply L'Hopital's rule a few times, but the limit of the original, let me go to the next page. So our original question was the limit as x approaches infinity of 6x squared plus 2x over 5x squared minus 1. So applying L'Hopital's rule, because we know we get infinity over infinity, we can take the derivative of the numerator. When we do that, we get 12x plus 2. Take the 2 to the front, subtract 1 from the exponent. And when I take the derivative of 2x, I just get 2 over 10x. And the minus 1 goes to 0. What happens when I take the limit as x goes to infinity now? So good. So the numerator we have, or the denominator, we have 10 times infinity, so we get an infinite value. In the numerator, we have 12 times an infinitely large number, which is an infinitely large number, and then we're adding 2 to that, so we still end up with an infinitely large number in the numerator. So we still have the same situation that we had before. So what I can do now is I can apply L'Hopital's rule again. So this is the same thing as taking the derivative again. So the limit as x approaches infinity. The derivative of the numerator, I just get 12. Derivative of the denominator, I just get 10. And now as x goes to infinity of a constant, I just end up with 12 over 10, which simplifies down to 6 over 5. which is what we would have gotten had we done the dividing each term by an x squared and then applying the limit. We would have gotten the same answer. So we could have used either approach. Sometimes we don't have the other approach, and we'll do some examples. So sometimes we have to use L'Hopital's rule. So let's do another one. Actually, before we do this one, let's do the next one because it's a little bit easier. Let's deal with this one first, and then we'll come back to the last one. So we have the limit as x approaches infinity of 2x to the negative 3 times e to the 2x. One thing that L'Hopital's rule needs is it needs a fraction. So is there a way that I could write this as a fraction? Well, the x to the negative 3, remember a negative exponent just means move to the denominator. So I could rewrite this as the limit as x approaches infinity of 2, that stays where it is, e to the 2x over x to the third. To use L'Hopital's rule, at least right now, we need a fraction. So I can take the derivative of the numerator and the derivative of the denominator. So what happens as x goes to infinity? Well, in the numerator, we have 2 times e to the 2x, so that goes to infinity. In the denominator, we also have x to the third, and as x goes to infinity, we get infinity. So because we got infinity over infinity, we can use L'Hopital's rule. And the last question, we were able to divide each term by the largest term in the denominator, but there's no way for us to simplify this in any other way. So the only option we have is to use L'Hopital's rule. So I can take the derivative of the numerator, the derivative of the denominator, and then simplify. So what is the derivative of the numerator? Well, the 2 stays where it is. And then what? Great, so I have an extra 2, because the derivative of e to the 2x is itself, but then times the chain rule says times the derivative of 2x, so I get 4e to the 2x. I'll simplify that in the next step. And in the denominator, I get 3x squared. So I have the limit as x approaches infinity of 4e to the 2x over 3x squared. So again, the 2 stays where it is, the derivative of e to the 2x is itself, but then the chain rule says times the derivative of the 2x, which gives me 2. So what happens now is I take the limit as x goes to infinity. Well, in the numerator, I have e to an infinitely large number, and you can always go to your calculator and type in e to the 2 times a very large number, and then just like we did when we were plugging in numbers before, you can plug in even larger numbers and you'll get that the numerator just keeps getting larger and larger, so that goes to infinity. What about the denominator as x goes to infinity? Very good. Also goes to infinity. So we're still at infinity over infinity. So we can apply L'Hopital's rule again. So we can take the derivative again of the numerator and the denominator and then see what happens. So let me go to the next page. So right now we have the limit as x goes to infinity of 4e to the 2x over 3x squared. And we're going to apply L'Hopital's rule again, which says we can take the derivative of the numerator and denominator separately. So in the numerator, I get another factor of 2 because the 4 stays where it is. Derivative of e to the 2x is 2, e to the 2x. And you could go right to writing that as 8 if you want. And in the denominator, I take the 2 to the front, so I get 6x when I subtract 1 from the exponent. So I have the limit as x approaches infinity of 8e to the 2x over 6x. So now when I apply the limit again, what happens? Very good. The same thing happens again. We get another infinity in the numerator and an infinity in the denominator. So we're still at the same place that we were, but what I notice is that if I apply L'Hopital's rule again and I take the derivative again, the denominator is going to become just a constant. So that won't go to infinity. So I know that the next step will be likely the last step, the last time I have to apply L'Hopital's rule. So if I apply this again, in the numerator I get another factor of 2, so I get 16 e to the 2x over 6. So now the numerator goes to infinity, but the denominator goes to 6, or stays at 6. So what is an infinitely large number divided by 6? It's still an infinitely large number, so we get infinity. So infinity, we can get that as an answer, we just can't make any conclusions if we get something like infinity over infinity. But in this case, we end up getting an infinite answer, which is okay. So the idea with L'Hopital's rule is we want to get a fraction. If we don't have a fraction, we're going to try to make a fraction, which is what we had in this case, because our function started out not written in fraction form, and we wrote it in fraction form. And once we applied L'Hopital's rule a few times, 3 times, we were able to conclude that the numerator goes to infinity, the denominator goes to 6, which means we are left with infinity. So now let's go back to that example that I wanted to do before. So we have the limit as x approaches 9, and in this case from the right side, which we'll deal with that in a little while, we'll talk about why that matters, of 1 over the natural log of x minus 8 minus 1 over x minus 9. So I have a limit. One thing I did want to mention is the limits so far, they've both gone to infinity as x goes to infinity. They don't have to go to infinity to use L'Hopital's rule, and in this case we will use L'Hopital's rule, but we don't have x going to infinity, so it doesn't have to. So here's what I'm going to do. I'm going to try a direct substitution. As we approach 9 from the right side, what's going to happen? As x approaches 9 from the right side, in the first term, in the denominator, we have natural log of 1 approaching from the right, minus 1 over 0 is what we end up with, which is not an answer. So here's what we're going to try to do. We're going to try to write this in another way so that we could potentially apply L'Hopital's rule, because right now we have 2 terms and we need 1 fraction in order to apply this rule. So let me just ignore the limit for right now. And just focus for a minute on rewriting this. So how can I get this to be 1 fraction? Well, I can cross multiply. You can think of it that way. So I can multiply an x minus 9 over here. And I can multiply a natural log of x minus 8 over here. So what I'm trying to do is get these on the same fraction. And when I do that, I can't just multiply the numerator, not the denominator, so that's what I'm doing. I'm just trying to get a common denominator. So that means over here, I have an x minus 9, and now they have the same denominator. So I can combine these. So in the first fraction, I have x minus 9 times 1. I'll just leave that as x minus 9. And then minus the natural log of x minus 8. And all of that is over x minus 9 times the natural log of x minus 8. So I just used common denominators to get them on the same fraction. And now what I have is one fraction, and I can try to use L'Hopital's rule. Okay, so now let me go to the next page and we'll deal with the limit. So I have the limit as x approaches 9 from the right, and we just rewrote the fraction as x minus 9 minus the natural log of x minus 8 over x minus 9 times the natural log of x minus 8. So if we apply L'Hopital's rule now, well, before we do that, if we tried to do a direct substitution, in the numerator we would have 0 minus the natural log of 1, so 0. In the denominator we'd have 0 times the natural log of 1, which is also 0. So if we just tried to do a direct substitution, we get 0 over 0. And this is one of our indeterminate forms. So what we can do is we can apply L'Hopital's rule at this point. So it says I can take the derivative of the numerator and then the derivative of the denominator and try to take the limit again. So in this case, the derivative is a little bit more complex than the last one. The numerator, I have x minus 9. So when I take the derivative of x, I get 1. The derivative of negative 9 goes to 0. And then what about the derivative of natural log of x minus 8? So remember the derivative of natural log is 1 over whatever's in those parentheses. And then times the derivative of what's in those parentheses. And in this case, the derivative of x minus 8 is just 1. So I'll go ahead and write it. And in the next step, I will get rid of it. What about the denominator? How am I going to take the derivative of the denominator? Great, I have to use the product rule. I have two functions multiplied together, so I have to use the product rule. So the product rule says the first function times the derivative of the second function. So the first function, which is x minus 9, times the derivative of the second function, so 1 over x minus 8, and then times a 1, just by the chain rule, and you don't need to write the 1. So the first function times the derivative of the second function, plus the second function, which is the natural log of x minus 8, times the derivative of the first function, and in this case, the derivative of the first function is just 1. So unfortunately, this fraction looks pretty complex. So let's go to the next page and try to simplify and see if it changes anything. So I have 1 minus 1 over x minus 8 in the numerator. The denominator in this first term, I will just combine this as x minus 9 over x minus 8. And then in the second term, in the denominator, I just have natural log x minus 8. So it's a little bit better than it was before. If I try to again apply a direct substitution, I'm going to end up with 1 minus 1 in the numerator, which is 0. And in the denominator, I'm going to end up with 0 plus 0, which is 0. So if I try to direct substitution, I still end up with 0 over 0, unfortunately. So here's what I'm going to do. I'm going to simplify this as much as I can before I try to apply L'Hopital's rule again. You could try to apply L'Hopital's rule now if you wanted to. It's just that the function is a little bit complex because we've got this fraction in the numerator and this fraction in the denominator that make it a little bit more complex than I would like. But you can go ahead and apply L'Hopital's rule now, or you can simplify. So just looking at the function, not dealing with the limit right now, I wanted to simplify this. The best way for me is to get rid of the fractions. Is there any way that I can get rid of the fractions in both the numerator and denominator? So I can always multiply a numerator and denominator by whatever I want as long as it's the same thing. So is there something that would get rid of the fractions in both the numerator and denominator? So if I were to multiply x minus 8 over x minus 8, which I can do because I'm just multiplying by 1, what would happen, and we still have to take the limit, I just left it off for right now because we're just simplifying this. What would happen is in the numerator, I could distribute the x minus 8 to both terms. So x minus 8 times 1, I get x minus 8. And then what happens in the second term when I distribute the x minus 8? Well, the x minus 8s would cancel. Good, and I'm just left with 1. So really in the numerator, I have x minus 9, which I'll simplify in the next step. In the denominator, when I distribute the x minus 8 to both terms, the x minus 8s cancel in the first term, and I'm left with x minus 9. And in the second term, I just have to multiply, so I have plus x minus 8 times the natural log of x minus 8. Okay, let me go to the next page and simplify. Just all I can really simplify at this point is the x minus 8 minus 1 in the numerator, and I'll put the limit back. So I have the limit as x approaches 9 from the right. In the numerator, I now have x minus 9, the x minus 8 minus 1. In the denominator, I have x minus 8 plus x minus 8 times natural log x minus 8. So at this point, again, if I try to do a direct substitution, I'm still going to end up with 0 over 0 because I have 0 in the numerator and then I have 9 minus 9 plus 1 times 0. So I have 0 in the denominator as well. So at this point, I can try to apply L'Hopital's rule again. So I take the derivative of the numerator. What do I get? Good. I just get 1. Derivative of x is 1. Derivative of -9 goes to 0. In the denominator, I have x minus 9, which, again, I get 1 for the x, and then the minus 9 goes to 0. And how am I going to take the derivative of this term? Great. I'm going to have to use the product rule. So I have the first function, which is x minus 8, times the derivative of the second function, so 1 over x minus 8. And then the chain rule says the derivative of that, which is just 1, so I'll go ahead and write it. And then plus the second function, natural log x minus 8 times the derivative of the first, which is just 1. So the good news is that there's a 1 in the numerator. So hopefully I can end up getting a final answer here. One thing that's going to happen here is the x minus 8s will cancel, leaving just a 1. So let me go to the next page. So I have the limit as x approaches 9 from the right, and I have 1 over 1 from the derivative of x minus 9, so right there. And then the second term I'm left with a 1, so plus 1, and then plus the natural log of x minus 8. And that was our last term here. So I have 1 plus 1 plus the natural log of x minus 8. So now as I take the limit, I can do a direct substitution because natural log of 9 minus 1, I get 0, because the natural log of 1 is just 0. So I'm left with 1 over 2. So the algebra in this section is pretty in-depth, so we have to work with a lot of rewriting fractions and simplifying as much as we can. It just makes it easier to take the limit. Like I said, we could have applied L'Hopital's rule again. Let me go back. Right here at this step, we could have applied it again. But the reason I wanted to simplify first is just because then I can avoid having to use the chain rule or the quotient rule if I don't have to. So what about the limit of x to the 3 over x? As x approaches infinity. So we have x to the 3 over x. So if I just have an infinitely x go to an infinitely large number, what happens to 3 over x? So what happens to the exponent? So for example, as x goes to infinity, what does the limit of 3 over x go to? So the x will go to infinity in the denominator, and then we have a constant divided by an infinitely large number. So what ends up happening is, good, it goes to 0 because we have 3 divided by a very, very large number, and that gets closer and closer to 0 as x goes to infinity. So what we end up with is infinity to the 0. And that's one of our indeterminate forms that we can't have. So this is something that happens a lot with L'Hopital's rule that we have to do. And we have to try to rewrite this in some way that will make it a fraction. So is this true, what I just wrote? Well, it is true. And the reason is when I take e to the natural log is in base e. And what happens is you can almost think of them as they almost cancel each other out. So I can take e to the natural log, and I just use 3 as an example. That's a completely unrelated to the 3 as e to the natural log of 3. Why would that be useful? Well, why it's useful is I can rewrite x in the same way. So I was able to rewrite x to the 3 over x as e to the natural log of x to the 3 over x. So why that's useful is log rules or natural log rules apply. So let me go to the next page for a minute. So right now what we have is the limit as x approaches infinity of e to the natural log of x to the 3 over x. You could also have this written if you wanted to, because x is what's being raised to the 3 over x, so you could have the 3 over x within the parentheses too. Both are the same. And do we remember any rules about when we had the natural log of a with some exponent, what we could do with that exponent? So we can always, with log rules, if we have our term, the natural log or the log, if our term has an exponent with it, we can always move the exponent out to the front. That's how logs and natural logs work. So by writing it this way, I can apply log rules to what we have here. So that exponent, 3 over x, I can move out to the front. So I have the limit as x approaches infinity of 3 over x, excuse me, I forgot the e, sorry, e to the 3 over x times the natural log of x. And now I have the limit as x approaches infinity of 3 natural log x over x as the exponent to e. Okay, so applying x going to infinity, that exponent is going to be infinity over infinity. So I can now apply L'Hopital's rule because this is going to go to infinity over infinity. Which means if I apply L'Hopital's rule where I take the derivative of the numerator and the derivative of the denominator, I have the limit as x approaches infinity of e. In the numerator, I have 3 natural log x. The derivative of natural log x is 1 over x, and the 3 just stays where it is, so I have 3 over x, or 3 times 1 over x. And then the derivative of the denominator is just 1. So really I have the limit as x approaches infinity of e to the 3 over x. What happens as x goes to infinity? As x, good, you're both right. So as x goes to infinity, 3 over x goes to 0. So I get e to the 0, and e to the 0 is 1. So I had to use some natural log rules on this one because in order to apply L'Hopital's rule, I need a fraction. And the only way to get a fraction in this case was to use this, the fact that, for example, I just randomly chose 3. 3 equals e to the natural log of 3. And you can always go to your calculator if you want and type in e to the natural log of 3, and it will give you that the answer is 3. So I took that I could rewrite x as e to the natural log x, and the exponent 3 over x was part of that. So I have e to the natural log of x to the 3 over x, and then I use log rules that say I can take the exponent and move it out to the front, which is what I did. I moved this 3 over x out to the front. So I have e to the 3 over x times x, and that's how I got the fraction. And then the exponent, when I take the limit as x goes to infinity, gave me infinity over infinity, but I could apply L'Hopital's rule again, and that's how I ended up getting e to the 0. Let's try another one. So we have the limit as x goes to infinity of 1 plus 2 over x to the 2 natural log x. And this question is really algebra heavy, so I will try to put as many steps as I can. So just bear with me, this one is really algebra heavy. So if I just take x going to infinity, in the parentheses, the 2 over x goes to 0, so I'm just left with 1. And then 2 natural log x as x goes to infinity goes to infinity. And 1 to infinity is, unfortunately, it's not an answer, it's one of our indeterminate forms. Which means we need to use L'Hopital's rule, or we can use L'Hopital's rule. So in order to get a fraction, we need to try and maneuver this function around in another way, kind of like we did in the last one. So what I'm going to do is I'm going to take the limit as x goes to infinity, and I'm going to use the e in the natural log that I just did. Because this has an exponent, if I try to bring in a natural log, I can move that to the front, and that will give me I can use the log rule. So I'm going to have e to the natural log of 1 plus 2 over x, and the exponent is 2 natural log x. So I was able to rewrite this function as e to the natural log of 1 plus 2 over x to the 2 natural log x. And now the whole point of doing that is now I can take that 2 natural log x to the front, because that's log rules. I can always move an exponent to the front. So I have e to the 2 natural log x times 1 plus 2 over x. Excuse me, I left off the natural log by accident, sorry. So 2 natural log x I move to the front, and that leaves the natural log of 1 plus 2 over x. So unfortunately, it still isn't a fraction, but the good news is that I can always write this as a fraction if I wanted to. So for example, I can take one of those terms and move it to the denominator. How would I move something to the denominator? What have I done before? Well, very good. I make the exponent -1, and you can move either term if you would like. I'm going to go ahead and move the 2 natural log x, or even just the natural log x if you wanted to. So I'm going to have e. I'll keep the natural log of 1 plus 2 over x as the numerator, and then to move the other part, I have 2 natural log x to the -1. So now I do have a fraction. And I know I said this already. You could have left the 2 in the numerator if you wanted to. It doesn't matter. Okay. So now I have a fraction, and now I can take the derivative of the numerator and the derivative of the denominator. It may help because we are going to have to take the derivative of the inside of those parentheses. So just before I deal with that, I'm just going to go ahead and write this. 2 over x is the same thing as 2x to the -1, just preparing for that derivative now. So what do I get when I take the derivative of 2x to the -1? Great. Very good. Excellent. I get -2x to the -2. And again, we're just going to need that in a minute, so that's why I wanted to get that ready now. All right, so let me go to the next page. So right now, here's where we are. We're at the limit as x approaches infinity of e to the natural log of 1 plus 2 over x. And we have moved the 2 natural log x to the denominator, giving it a -1 exponent. So that's where we are right now. So L'Hopital's rule says I can take the derivative of the numerator and the derivative of the denominator. So in the numerator, I have a natural log function. So remember, the derivative is always 1 over whatever is in those parentheses. So I have 1 over 1 plus 2 over x. And then times the derivative of the inside parentheses. And that's why we just found that derivative. So times -2x to the -2. In the denominator, what rule do I have to use to calculate this derivative? Well, I have a function being raised to an exponent, so I have to use the chain rule. So I'm going to take the -1 to the front, keep what I have in the parentheses, subtract 1 from the exponent. Anything else that I need? So the chain rule says that I have to take the derivative of the inside parentheses, so the derivative of 2 natural log x. Excellent, 2 over x. So right now we've applied L'Hopital's rule. Everything is not simplified in a way that's really useful, so let's take a minute to simplify. So all of that fraction is the exponent of e. So in the numerator, just looking at this part, the -2 is the only term that can go in the numerator. The x to the -2 actually goes to the denominator and becomes an x squared. So I've put the negative 2 in the numerator, I've moved the x to the negative 2 to the denominator, and then that's times 1 plus 2 over x. In the denominator, the negative 1 times the 2, I get a negative 2. And then everything else is in the denominator, so I get x times 2 natural log x squared. You could have also moved that 2 natural log x up to the numerator, and we'll do that in a minute. So we have a complex fraction here. The good news is we can simplify some items if we wanted to. So we could cancel. If you want, you could also, whenever we are dividing, it's really the same thing as multiplying by the reciprocal. Actually, let me go to the next page. I don't think I'm going to have room. So right now we have the limit as x approaches infinity. We have negative, e to the negative 2 over x squared times 1 plus 2 over x. This is just where we just got to. And then that is all over negative 2 over x times 2 natural log x squared. So we have a pretty complex fraction. But what I can do is I can flip the denominator and multiply. So I have the limit as x approaches infinity, e to the negative 2 over x squared times 1 plus 2 over x times x times 2 natural log x squared over negative 2. And there's quite a few different ways that you could simplify this. It's just a matter of preference. So if you would prefer, you could have canceled these negative 2's. There's, like I said, there's a bunch of different ways. So now what happens is the negative 2's cancel. Is there anything else that cancels? Good, we can cancel this x, and that cancels one of those x's. And like I said, I'm just trying to simplify as much as I possibly can in hopes that something will simplify. And then I can more easily apply L'Hopital's rule, because I would much rather apply, if I have to apply L'Hopital's rule again, I would much rather apply it to something more simplified rather than that. Okay, so simplifying again, the limit as x approaches infinity, we have e. In the numerator, we have 2 natural log x squared. In the denominator, we could distribute this x here to both of those terms, and that would get rid of the complex fraction. So we would have x plus 2. So it's slowly starting to simplify a little bit more. And again, if I take the limit as x goes to infinity, that numerator goes to infinity over infinity, and that we can't have. Or the exponent goes to infinity over infinity, and that's what we can't have. So what I can do is apply L'Hopital's rule here. So I have the limit as x approaches infinity. E stays where it is. Take the derivative of the numerator. So I take the 2 to the front, keep what I have in the parentheses, subtract 1 from the exponent, times the derivative of what's in those parentheses. And what about the denominator? What is the derivative? Great, I get 1, which has simplified this fraction quite a bit. So in the numerator, I have 2 times 2 times 2, so I get 8. So I have 8 natural log x times 1 over x. So let me go to the next page. So I have the limit as x approaches infinity of e to the 8 natural log x over x. So that's because our exponent was 2 times 2 natural log x, and then times the 2 over x, all of that over 1. So that's what we had on the last page. So what I did is, over 1, I can just leave off. So I have 2 times 2 times 2, which gives me the 8, and the natural log x, and then since it's over x, I just wrote the entire fraction over x. And unfortunately, we're still where we just were, where this goes to infinity over infinity. But the good news is when I apply L'Hopital's rule again, that denominator is going to go to 1, which means that hopefully I'll be done at that point. So if I apply L'Hopital's rule again, and sometimes when I apply the rule, I write LH over the equal sign. It just indicates that I applied this rule again. So I have the limit as x approaches infinity. What's the derivative of the numerator? Derivative of 8 natural log x. Great. So I have 8 over x. And what about the denominator? Very good. I get 1. So 8 over x over 1 is really just 8 over x. So I have the limit as x approaches infinity of e to the 8 over x. And as x goes to infinity, what happens to 8 over x? So the limit as, whoops, x goes to infinity of 8 over x. Good, very good. We have a constant divided by an infinitely large number, which goes to 0. So we again end up with e to the 0, which is 1. It's not always the case that you end up with e to the 0 when you use the e to the natural log rule, but it is a common answer that you get fairly often, but it's not always the case. Okay, so like I said, the algebra in that one was pretty heavy. There was quite a bit of simplifying and moving things around in hopes of something canceling. But what we did was we used the fact that e to the natural log of our function makes our function a natural log of an exponent, so we can move the exponent out to the front. And that was what we did. Let's go to another one. Okay, so we have the limit as x approaches 4 of x minus 4 over x squared minus 4. So what happens when I apply a direct substitution? And remember, anytime I can apply a direct substitution, I do. So as x approaches 4, what do I get in the numerator? Good. I get 0. What about the denominator? Very good. So is this okay as an answer? Yeah, it is. So I wanted to show you this one because I don't want us to always want to apply L'Hopital's rule, because in fact we can't apply L'Hopital's rule in this case. If we tried, we would get 1 over 2x. So if we did apply L'Hopital's rule and took the derivative of the numerator and denominator, in the numerator we'd get 1, in the denominator we'd get 2x. So when we take our limit, we'd get 1 over 8. And that's not the answer. The answer is 0. So L'Hopital's rule only applies, you can only use it when you get one of your indeterminate form answers. And that's the table listed at the very beginning. One of these answers. This is when you can use L'Hopital's rule. If you get 0 over 12, that's okay. So in the last example, let me go back to it. We just ended up getting 0, and that was it. Let's do one more of these. So I have the limit as x approaches 0 of sine x over x. So like I said, a direct substitution is usually where I start, because if it works like the last one, then I'm done and I don't have to do anything else. What happens when I do a direct substitution here? Excellent. I get 0 over 0. So 0 over 0 is not an answer, but it is an indeterminate form answer. And the nice thing about this question is we have a fraction already. So there's really no reason to try to rewrite it using the e to the natural log because we already have a fraction. So I can just directly apply taking the derivative of the numerator and the derivative of the denominator. What happens when I take the derivative of sine x? Great, I get cosine x. And what about in the denominator? Very good, I get 1. Now can I try a direct substitution? Or if I do try a direct substitution, what do I get? Very good. Cosine of 0 is 1. So I get 1 over 1, which is just 1. So I wanted to do this example last because I don't want us to think that we always have to apply the e to the natural log and see how that goes because those get pretty complex. We can, in this case, we already have a fraction. It's already sine x over x. So what I can do instead is I can just apply L'Hopital's rule directly. I don't need to rewrite as e to the natural